in the bottom of the screen.
Okay.
All right, there's the OK screen. Now, if I hit the CAD button, we switch to CAD screen. If I hit the rectangle button, we switch to the rectangle display, where we can see the whole chip. If I zoom out a little bit, or most of the whole chip. Actually, it's possible to zoom way out and get the chip down to true size, but not practically. The interesting thing is to zoom in to where you can see some of the geometry of the chip.
Why don't you zoom back a little and show what each of the different layers are?
Okay. Here's a region of the stack, and there is, with the second metal ground off, there are just the diffusion and wells. There is just one region of diffusion, and the other region of diffusion, P versus N diffusion. There are just the wells, and there are all the diffusions together with the wells. There are just the substrate and well substrate contacts. There's just the poly. There's just the metal. And there's the metal plus contact. And there's just second metal, and there's second metal plus contact. And there's all of them together. And there's the second metal removed. So you can see these. Accidentally hit the rectangle button. The reason the rectangle button is in red is to warn you that if you hit that button, the computer's going to be busy for 10 seconds recomputing, re-extracting all the geometry from the tiled representation. And blink, now it's finished. So it takes that long to compute 80,000 rectangles, which is fairly middle and fast. Let me zoom in again here. Now you can see a couple of interesting things. Transistors are regions where poly crosses diffusion, where red crosses green. So this is a transistor. This is a transistor. This is an N transistor because its background is black. It's a P transistor because its background is greenish. It is in the N well. The transistor is controlling the flow of current from here to here. So this is the transmission gate. These pair of transistors constitute a transmission gate in which current either can go, signals can either go from 0 to 5 volts or 5 volts to 0 with equal facility. And basically these two transistors control a switch between these two metal lines. Now this is a very large transistor, physically large. But its geometry is such that it only conducts 1/10 the current. This one does. And likewise, this transistor only conducts 1/10 the current of that one. If we switch to this mode, then they get more clear. Here's another pair of transistors down here that constitutes an inverter. These two inverters, cross-coupled inverters, constitute a latch. And this is one of the transmission gates enabling input into the latch. So what we're seeing on the screen now is just about 1 bit of memory. Control lines tend to be silver, and the buses tend to be blue. And this whole thing constitutes about 1 bit of memory. If we zoom out a little bit, now you're seeing 2 or 4 bits of memory, and now you're seeing about 6 bits of memory, and we get out here to where we're looking at something like 1,000 bits of memory. So this entire structure here is the region of the data stack. It's 16 bits, 16 registers by 20 bits, so there's 320 bits of memory right here. Here's the ALU. for the processor. And if we go up a bit, we find the return stack here. And instruction registers are in this region. Registers are organized horizontally, like so. So the bits 0 to 20 stretched across the screen horizontally. In the center you find big transistors to drive the control lines for all of these bits. And you hear some random logic instruction decode to select the control lines for those devices. Floor. One reason I'm sitting on the floor is all this clutter you see around me, that I don't have a desk large enough to accumulate all of this stuff. The floor is a perfectly reasonable place to be. In addition, in case of an earthquake, none of this stuff has any distance to fall, so it's not going to get injured.
Okay, now I need to...
Okay, here we are back again. This is the return stack, this scale. I'm struck by the asymmetry between the right side of this and the left side. Right side has 10 bits and left side has 11 bits, and I guess that extra bit tucked on the edge is, I can count these things. 1, 2, 3, 4, yeah, I must account for all the difference. Okay, here is, here's the memory processor, which is spread out a little bit. I've been moving things around and I haven't compressed them down again. Here's the video coprocessor here with its output pad. A lot of extra space in which I can use for increase the depth of stacks or something. This is the network. So this is the analog processor here, and the network processor above it. Network processor here, and here's the parallel port, which is attached to the pads at the top of the chip. Go to, oh, we haven't even looked at the
That's right.
at the tiled representation. This is the tiled representation of the chip as distinct from the geometric representation we were looking at before. They're saying the same things except they aren't scaled to the actual geometry required by the fabricator. They're more or less the right thickness of lines, but only approximately. This is where I work and edit and simulate the design. And then later the rectangles are generated to actually provide the output for fabrication. But here I have the ability to simulate the behavior of the chip. If I hit this button, we are now reset to all signals start at 0 except for these 3 pads which represent 5 volts. And here we're looking at 4 traces as they vary in time. As power has ramped up from 0 to 5 volts by now, and you're seeing the 64 pads of the chip change from +5 to ground as time goes on. So we can monitor 64 signals here and 4 signals in great detail here. Each of these squares is 8 nanoseconds across. Typically, the first interesting event is going to occur about here, where the first memory access has been completed. You see these signals varying from ground at the bottom, 5 volts at the top. Now the address lines have been established correctly. This is the SRAM select bit, which has gone low. As a consequence of that, this data word has been read, 8-bit data word has been put on the input lines. It represents a semicolon, so that I will switch from SRAM to DRAM. Now if I stop this process and go back to the tiled layout, we're now in a position to see the bright red signals have got 5 volts on them, dark red signals have got ground on them. So we've established the signal levels for 2,500 signals on the chip. And I can pan through the chip looking at the state of all the interesting signals and deciding whether or not things are correct or not. So this is a digital representation of the logic levels of the chip. If we go back to the simulator, here we get an analog representation of 4 of the signals, which are particularly interesting.